you know what I like to do, Wayne?
What's that?
Not kill my goldfish.
That is a brilliant thing to not do.
Yeah.
But I keep killing mine, so
Yeah.
what's your secret?
Oh, I just add loads of buffer solution.
That is the new craze
Yeah.
in Fish Magazine Weekly that I just made up. If I walk into your house with a beaker full of acid and I trip over your cat and I tip it all in your fish tank, you know, obviously.
Yeah, that's what you do, right?
I do that by
and
accident.
they're fine.
They're fine, that's great.
By accident every day.
Yeah, so
Yeah.
it's amazing. Your house is amazing. I mean, you've even trained the cat. Firstly, trip me up, practical joker.
It's a good one.
Love it, I love jokes. Secondly, it doesn't eat the fish.
No, I don't, it's amazing. If
Wow.
only it was real.
Yeah.
Wish I had a house. Buffer solutions.
Something new. So, if we had a reservoir of water with lots of fish in it,
Yeah.
rather than a tiny fish tank, they have natural buffer solutions in them. What does a buffer solution do?
Well, Wayne, it minimises the change of adding excess alkali or acid.
It does indeed. So, if there was a small acid spill in a reservoir, a small one, if it's huge and it's not going to make a difference, but if there's a small one, rather than all the fish dying, it will minimise that change so that it won't drop too much in pH.
Yeah.
Natural.
That's pretty
Natural.
great. You have to know how that happens, though.
Yeah, unfortunately, chemistry likes to
Test you on chemistry.
Yeah.
I can't believe those guys.
Unbelievable.
Yeah. So, basically what you have is you have a weak acid.
Yeah, this is a weak acid, that's why
Yeah.
it's reversible. I'm
Yeah.
expressing it, A could be the rest of the chain.
And, yeah, as Wayne said, it partially disassociates and it forms those two things, that being the conjugate base.
It is indeed. So it's weak because it's forming an equilibrium solution, a reversible one. And also, this A could be, it's normally huge, so it doesn't fully dissociate, it partially dissociates.
Yeah, so we've got this, we haven't just got this, have we?
We haven't.
You also have the conjugate, well, the salts, the conjugate salt forming more of the conjugate base. Let's explain that better, as an example.
We would, yeah. Rather than HA, let's actually do one.
Okay.
So it's a weak acid, and the one they like to see you do is ethanoic acid. The same thing will be true for methanoic acid, but they like ethanoic. So
Alright, so let's do the same thing. So you have ethanoic acid, which is CH3COH.
You also have the salt of this.
Yeah.
Which is the same thing, but at the end it's O minus Na plus. It's a salt with Na. So make sure it's minus and plus there.
Yeah, that is important.
This is going to set up an equilibrium thing.
It is forming essentially what we do on the top, but the two things on the top are in a different order. But we have our A minus first, but that is, yeah, it's clear to the minus.
Yeah, so it's got the rest of it minus and a H plus.
But when we put this in our reservoir or any water, it will separate into its ions.
It does indeed. So one of those ions is the conjugate base, it's the same thing, this CH3COO minus. This time it's not a reversible reaction.
Yeah.
So it's CH3COO minus again, plus Na plus.
But this isn't very important, so you can pretty much ignore that for now.
In terms of buffer solutions, that does nothing. It may well do other things within the river system or whatever, but in this, not.
Yeah.
So, a few things to notice. Firstly, overall, we're going to produce another equation. These are just the two separate things. When it's got this reversible, we need to ask ourselves, where's the position of equilibrium? Is there equal amounts of this and both of these?
There's not.
There isn't, it's a weak acid.
Yeah, and it's also very far to the left. There's much more reactions than there are products.
So if I had a beaker of this, most of the stuff in there would be the actual acid itself. Relatively little would be the ions, barely little it would have split.
Yeah.
So we have little amounts of this and this, but on this side,
we just make
loads
this.
of this.
We make loads of this. What you end up with is a lot of our acid we have at the start.
Yeah, because very little of this split up, so we've got loads of it left.
Loads and loads. We also have a lot of this.
Yes, because we're adding the little amount here with the loads of amount there. So we get CH3, COO minus.
And then we have a tiny amount of H plus.
Which we're going to do in orange.
There you are.
He's a joker, but let's write it a little bit bigger. As much as I appreciate a joke.
There's not very much of it.
So, there isn't very much of it.
No.
As a general thing. So, what happens if I accidentally accidents happen, don't they?
Yeah.
I accidentally spill a truck full of acid in a reservoir.
Yeah, that would be bad, but good for teaching chemistry.
Really good for teaching chemistry.
So, you add acid.
Yep, so I'm going to do this in red. This is all in red, acid in red.
First, where's the equilibrium move? Well, it's already even further across than it was a second ago because of loads of this.
Yeah, we've got even more of this, that's worth mentioning. So it's shifted even more to the left.
Yeah. When you add acid, it does even more. So what you basically, the easy thing to come out in buffer solutions is to always think about our H+. We're adding more H+.
We are indeed.
And Le Chatelier's principle will move to oppose the change.
Yeah.
It'll move in this direction here.
Exactly. It's worth mentioning, what about the other two things? What's going on with them? If you add more H+, this load of this minus ion here is going to mop up as much of the H+ as possible. And when that happens, it's going to form more of this.
Yeah, this is why
reactant.
everything moves.
Yeah. So the decrease in this sort of matches the increase in this.
Yeah.
So overall, we can just think about this, which is why Triv can use Le Chatelier's principle and say it moves this way, the position.
Yeah, so you have less acid and less change. How about an alkali then?
Okay, let's do it. Have you got an exciting colour?
Well, I just use orange, but I think I should use purple.
Yeah. So alkali, what it's going to do is it's going to try and mop up the H pluses. That's what it tries and does. It tries and gains a proton. There's a proton acceptor.
Yeah, so just say we're adding an OH.
So if Triv chips a truck full of alkali in, not the same river.
No, different, yeah.
Otherwise, terrible.
Yeah.
If he chips a load of that in there, it's going to try and mop up these H pluses.
And it will do rather successfully, but then the reaction will then make more of these, therefore move in the other direction.
Exactly, so it makes sense that it would be the opposite anyway. There is actually, because it's water, a reservoir is water, it's not all this buffer solution, because that would be weird.
Yeah.
There's water in it as well. Some of the water does break up into H plus as well. So there doesn't say it in most chemistry textbooks. If you look online, it will say some of the H plus from the water is also used in this.
Yeah.
So it's just worth mentioning. It might be a mark in your exam, perhaps.
And that's basically how buffers work.
It is
As
indeed.
a general thing. But you also have to work out a few more equations.
You do, unfortunately.
Yeah. So we have one of our favourite constants, the acid dissociation constant.
Yeah, of course it's going to come into it because acids are dissociating.
Yeah, so
oh, sorry, actually, I won't hook that up.
we might need that. It's to do with weak acids dissociating. Well, actually it's to do with both, but often you write it with this one.
Yep. So it's Ka.
Yep. Car.
Car.
Yeah.
Very good. It's a car.
Yeah. Thanks, Wayne.
So we've got H plus.
Yeah. And we have our A minus at the top.
So it's products over reactants.
Yeah, that's how it works. So yeah,
HA.
more or less self-explanatory after that.
And often what we'd need to do is work out the pH. That's a question OCR loves. They love working out pH. So to do that, we're going to need H plus. So often with buffer solutions, you're going to have to reorganise this.
So that's relatively easy done.
It is. H plus equals
Ka times Ha over A.
Ka HA all over A minus.
Yeah.
Just like that. So that's worth mentioning. If it asks you to work out the pH, you're going to be using this. This is actually just a recap of an earlier video.
Yeah.
So it's just, we don't need to go into it in too much detail.
No? Yeah, you know what to do next, hopefully. If you don't, mind.
Check out our video.
Yeah, check out the videos, that works too.
So, reservoirs, that's good. Fish don't die. Is there any other good things though?
Well, it's used in nature a lot in blood, it's present.
Indeed, and that's really important because the pH of blood can differ very little before you sort of get problems.
Yeah, so it's quite a tight buffer there.
It is, and that's another natural buffer. I think it's H2CO3, something like that.
I think so.
But there is a buffer in blood, so it might be worth mentioning that's where they're used naturally. And I like blood.
Blood's, I like it inside me.
Oh yeah.
I less like it elsewhere.
Yeah.
Yeah, it's not a good, say, painting tool.
No, not since the 50s. Anyway, so that's buffer solutions.
Yeah.
And I think that's it in a nutshell.
I think it is, so I need to buy some goldfish and a cat, and you need to kill my goldfish, right?
Yeah.